CIA is recording our meeting. So what if I had, let's say, cosine of tangent of x minus 3/4. Sure, I like it. Nah, do I like it? Not really, but oh, too bad. Now, you do not have to do it this way, but this is a specific request. And this is the way I kind of showed you, but you don't have to do it this way. So I would rewrite this inside. I would make this like denominators. And now I can draw the triangle where this is the angle. And there is tangent, so that would be 4x minus 3, and this would be 4. Is everybody with me so far? Okay. So remember, inverse trig functions are angles that you can make live in a triangle, and this is the ratio of the appropriate sides. And now I could use Pythagorean theorem. It would be plus 16, right? And then what is that? That's 16x squared minus 24x plus 9 plus 16 plus 25. That's neat. Square root. And now I can make the cosine of that. It would be 4 over this mess. And then there was a really good question somebody else had earlier. So again, that's not the only way to do this problem, but that's, I don't know, that's a pretty good way. Somebody had a question earlier. Do you need to rationalize this? Always if there's a number in here. Not always if it's a variable expression. This is acceptable to stop here. In general, it's not convention to go forward and rationalize something like this just because. There's a few different reasons, but if there's numbers in there and no variables at all, then you rationalize it for sure. Okay. If you want to rationalize everything, including stuff like this, go ahead. It's not wrong. It's just extra shit. All right. Anything else, guys? How far have you gotten in homework? I'm always curious. Hopefully you got enough of chapter 8 done that you're ready for the quiz today. And in case you didn't notice, the quiz is due Wednesday morning. So that I did that so I could be nice to you and to me, so I could meet with you tomorrow night. And the quizzes are not graded yet. There's no way in hell I would have done it anyway if I would have made it due tomorrow. So I might as well give it till Wednesday morning. All right, maybe. Anything else? Anything else from homework? All right, I'm going to take that as a good sign, being optimistic. Okay, I want to show you, this is nothing major, but just real quick, since I did this, I reorganized the modules a bit. So I added Unit 9 in, and I kind of pulled down some stuff that was sitting in Unit 8 that deals with identity stuff, because 9 is all about identity stuff. So that's in there now. I added a place to turn in some 9 homework, right? Let me see what else. I think that's it. Oh, dadgummit. Chat. No. 38 on 8.3. All right, let's take a look. So I got a question. 38 on 8.3. Let me look it up real quick. And I'll share this screen. Sure. See, 38 is this guy. Oh yeah, so that's a lot like the one we just did. right? So let's see. Let's try a little bit of sitting down here. So 38. This is the one you're talking about, right? Person? I can't remember if you're 38A3. This is the one. Yeah, okay. So just to really make sure you understand why I can look at this and immediately draw a triangle, because the output, what is the output to an inverse trig function? Geometrically, physically, what is the output?
An angle.
An angle, because the input to our trig is an angle, so the output of an inverse trig is an angle. That's an idea of inverse functions always. The input of the function is the output of the inverse function. So this is going to be some angle. So watch what I can do. I can take the cosine of both sides. There is some interesting stuff about domain that I don't know if anyone's picked up on. They do make a big deal out of, is it true that these can cancel? Not always, but there's these hidden domain problems. So let me speak to that real quick. If I write something like this down and I start messing with it, there is an assumption that I am living with. X cannot be anything it wants to be. There are certain limitations here. Same thing happens when I write this down. There are limitations on X. I don't have to expressly write them down. I do have to go back and be able to tell what the issue is if I have to do more with the problem. Are you guys with me? So I'm working with this algebraically with the underlying assumption of a domain that I'm not worried about at the moment, but I have to know, I got to go back and take a look if it becomes that way, but it's not an issue yet. So now I know the cosine of this unknown angle is 1 minus x. So I can set that triangle up. Is everybody cool with that? I try to get us to the point where I don't do any of this shit right there. I can see this, and I can automatically make that triangle. Can't get words out of my mouth. That's a bad sign. Automatically. There it is. And now I can answer the question by figuring out this last side. Is that cool? Was there a more specific question on that? Okay, gotcha. Cool. I like it. Anything else, guys? Anything else from homework stuff? All right. I'm going to clear this away. Oh, here's something. I know you already did this problem. So 36 on 8-2. All right, let me see. It is never wrong to ask a follow-up question, even if I've done the question already. That is nothing wrong with that. Oh, shit and a half. Where'd you go? This one, 36? Oh, yeah. Well, no. Sort of. So the first thing to realize about this problem, I sort of remember doing this, is they've written it kind of evil. Do I shift down 3? No, I shift down 15. Right, that's one thing to realize. I don't know if that's part of the question. The other thing I want to ask you is, what is the period of cotangent normally? I said that in a strange way, but there's no shift to the period, right? So what is the period of cotangent?
Pi.
Pi, 11. So cotangent and tangent have a period of pi. All the other ones have a period of 2 pi. I like it. And this one doesn't shift because there's no multiplier here. It's just a 1. And then there's a phase shift, right? Back pi over 2. So I'm not sure what the specific issue was. What does cotangent normally go from to for the base cycle? You guys remember? All right. Here's a little connection for you. Well, let's see. This connection requires you to know something. So the inverse sine, what is the domain? I'm sorry. What is the range of the inverse sine?
-1 to 1.
No.
Sorry, that's the inverse. Sorry.
Yeah,
so
inverse.
It would be -2 pi to 2 pi, or
No.
negative.
This is a good question.
pi.
I love it.
-pi/2 to pi.
Yes. It's related to the idea, I'm sorry, this is inclusive, that we had to restrict the domain of sine so that I could create inverse sine. This blue on red is probably not good for the eyes. I'm sorry. What does this have to do with ending? So I'm trying to give you a way to remember certain things. So this is kind of a long arc here, but let me see if this goes somewhere. I always remember tangent goes like sine. What do I mean by that? Tangent of pi over 3 is, now stay with me, stay with me. I have no idea how you crammed this stuff in your head, but for anybody who's done it the way I suggested, tangent's going to go like sine. Sine, wherever sine is bigger, tangent's bigger. So tangent's main outputs are √3 over 3, or 1. I don't know if anybody's noticed that. For the angles, we have to memorize, and of course, 0, right? So tangent follows sine. So notice how sine goes from -pi over 2 to pi over 2. Tangent goes from -pi over 2 to pi over 2. I'm sorry. That's where tangent kind of lives, the core cycle of tangent. Cotangent, so remember, cosine inverse has a range of 0 to pi. Cotangent is going to go from 0 to pi. I have no idea if that helped anybody. Or you could just memorize that tangent lives between -pi over 2 pi over 2, and cotangent lives between 0 and pi. Whatever works. Whatever works. So this is where cotangent normally lives, right? And it's kind of like inverse of tangent. So then I got to shift it back pi over 2. I got to move it down 15. And then the 5 is going to show up at the quarter marks. This would be 5, and this would be -5, right? For example. And then you shift it around. Does that help at all? Without any further specific questions, I don't know what else to say. Is that all right? What is there something more specific you had trouble with? Okay. And just make sure this is definitely not the answer. The only thing I applied was this. You still have to shift it back, and you still have to shift it down. Okay. All right. I like it. Anything else that I could use inappropriate colors on top of other colors for? Let me take that away. That was kind of painful. All right. All right, I don't see anything else. So let's go back to where we left off. Which I will admit, I will tell you this, I don't say this often, but this is kind of boring. You guys are like, dude, you're behind. It's been boring for a while. How many questions would the quiz have? I don't know. I could look at it. Let me see. Oh shit. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That's on the first page. No, I'm joking. That's 8 total. Yeah, it was funny, Jeff. Really funny. All right. Is that all right? So the quiz has 8 total questions, meaning I'm counting A, B, C, D. It's not 8 questions, each with their own A through J, right? Okay. So we are collecting, I identities. We're collecting these identities. In case you weren't here last time, I want to remind you. Here, let me see if I can pull this over. All right. Can you see Canvas again? Anybody?
Yes.
Thank you. All right. So here are the things you have to memorize. Everything above the black line here. Everything above this dark black line you have to memorize. Law, cosines, law, sines are the two things we have not talked about above this black line. Half angle stuff we talked about last time, right? And this stuff I think was the time before that, if I remember correctly. And there's your sum difference stuff with the cosine being an asshole. And see cosine's an asshole down here too. Well, cosine's such an asshole. I'm going to very quickly go over these. I'm not going to spend much time. These you don't have to memorize. They're a little bit boring. They're not like unimportant, but they're not the most immediately useful identities. That's how I'll put it. And we always have the fact that there are an infinite number of identities. So we sort of have picked the most important ones, and these are sort of the second tier down here. Okay. Hopefully that makes sense. And then even some of these, you don't have to memorize each one because you can build some off of the other ones. Okay. So come into the book. Here's something, well, this is old news. Let me see. We did the double angle stuff. We did that already. What I want to get to is, am I in the right place for, all right, here's the, all right, so what they call reduction formulas. And let's see if you see why they call it reduction formulas. So one thing I want you to notice is this work they did to get here. If I took a square root of both sides, I would have the half angle formula. It just isn't written as a half angle right now. Does anyone see that? So if I made theta alpha over 2 like we did that one night when we got the half angle formula, that's the half angle formula. That's all that is. But do you see why they call it reduction formula? What's the power on the left-hand side? What's the power on the trig function here? First power. What's the power on this side?
2.
Second degree, right? So this is what they call power reducing. If I have a squared cosine, I can rewrite it as a non-squared cosine expression. Not the most immediately useful thing. Am I saying I've never used it? No, I'm definitely not saying that. But it is nowhere near as often that it requires me to memorize it. That's why I don't have, I do have this memorized sort of because it's just the half angle identity. All right, hopefully you guys are with me. So some of these are unimportant because they're basically stuff I've identified as something else. All right, the half angle identity is more immediately important. Tangent stuff you really never have to memorize. I could kind of recreate them as I need them. So here's the reduction formulas. And again, I really want you to notice they are just the half angle identities, not square rooted and not written as half angles. That's all they are. Okay. So the ones that are even less important, blah, 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 blah. All right, these are all nifty. Those are the half angle formulas. I love it. All right, where are you guys? Oh, good. It must be in the next section. Okay. So let me tell you this. If I were going to do this chapter 9 homework, I would definitely have that green sheet of laws sitting next to me. And as I do the problems over and over again, I might start to get them in my head. Or if you're a person like me, how did I memorize stuff? I'd have to write it and 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 never look at it again and be in my head. So, because I'm very what is it called? I can't remember.
Tactile
I have to work with my hands. Huh?
Tactile learner.
Thank you. Okay, tactile. I love it. I thought it would start with a K, but I don't know. Kinesthetic. Kinesthetic. There it is. Thank you. I was thinking copacetic. I'm kinesthetic. Is that copacetic? Let me think. All right. So as I'm doing these problems, I'll have that green sheet sitting next to me so I can reference it as I need. Some of these are very specific. Obviously, you want the double angle formulas for these. Sometimes I'll tell you exactly what to use using half angle formulas. Thank you. Right? And then you'll have, let's see if this section has what I'm looking for. Stuff like this is a little bit open, but not terribly. I mean, you hopefully can tell this is in the form of an identity pretty directly. Then you have the prove the identity questions. Those are the ones that might sometimes be a little less immediately obvious. But still, don't look, let's see, how can I say this? Look at number 34. The first step for any identity proof is to pick a side to start working on. Both sides are a little promising here because this side is an algebraic thing I can do. And this side, I should know the identity for sine of 2t. So maybe this is a problem I could kind of work with both sides. You guys, so this side is not even a trig idea. It's just freaking square this thing. Is everybody with me? So it's not always immediately an identity you're going to apply. Sometimes it really is get the like denominators and put the fractions together, or square the thing, you know, FOIL it out, whatever. So notice this. This gets pretty quick. If I do this side, I'll very quickly see something interesting. So if I FOIL this bad boy out, I love it when it's a T, sint minus cost. I'll get, and have I shown you this? This kind of hurts me to write this. Have I shown you how we write this, especially when there's no cosecants and stuff? This is sine and cosine. So then I get s squared minus 2cs plus c squared. And what's sine squared plus cosine squared?
1.
And what's 2 cosine sine? Or 2 sine cosine even? Somebody remember? No? Not yet? So I only had to work on that one side. I've got it. Oh shit, what did I do? Oh, no 2 there, Jeff. Jeebus. now I got it. Except a T. Oh well. Bam! It's a T now. So be really careful about doing this. I try not to do it too much because people try to use it when there's sines and secants running around and you forget which S is which, and that's bullshit. So you don't want to use it too much. It's when you have only sines and cosines, it's just a quicker way to write stuff down. And, you know, even tangents, little T's in there. You guys with me on that? A little bit. Something like number 36. Oh, let me see. I got a chat here. Oh, all right. So what happened here that was it because I wrote things with S and C? Did that confuse anybody? No? Okay. Let me see. Here we go. Another chat. Just like identities. Oh, yeah. That's what we're going to do. We're going to do some more. Okay. Trust me. I understand. Identities get freakadelic. So look at 36. It looks like it looks like this would be the smart place to start. And this is one of the ones I said you didn't have to memorize. Right? So you're going to want to look that up on your little green sheet, right? You can do the tangent double angle, and so this is going to be 1 over that. All right, let's do that together. Let's look this up. I'm going to take this away. Oops, I got a chat coming in. Oh, all right. All right. Well, let's take a step back. All right. Let me clear all this away. Okay. So let's all start at the same place. We have proven, for example, that sine of 2 theta equals 2 sine theta cosine theta. We've proven that. If you forgot, well, first off, does anyone remember what sine of a plus b is? And again, if you don't have it memorized yet, okay, have this bad boy, the trig loss thing sitting next to you. Go ahead, sorry. All right, so let's go through this again.
Sine A, cosine B.
Yeah, because sine is the nice guy. Sine says, let's take turns, cosine. And you got a plus sign there? Okay, I'll keep it a plus.
Plus. Yep.
And now,
Sine B, cosine A.
good. They each get a turn. Jeff. If Jeff could spell. I can't even spell a 3-letter word. That's good. So they each get a turn. Sine gets A and cosine gets B. It stays plus. And then sine gets B and cosine gets A. Right? And the alternate to that is what's cosine of A plus B? Cosine's an asshole. So me, cosine A, cosine B. Now I'm done with my turn. Plus, screw you. I'll make it a minus. Go ahead, sine. It's your turn now. And sine's like, thank you. Cosine, major asshole. Sine, major milquetoast. Right? Love the word milquetoast. Look it up, kids. MILQUE toast. That's how I memorize those. And then if that's a minus, that's a minus. If that's a minus, that's a plus. That's the only other. Then there I've got 4 things memorized easy. Okay, I like it. How are we doing there? And then don't forget what we did was, well, what if I have sine of 2 theta? Well, that's sine of theta plus theta, which is sine theta cosine theta plus sine theta cosine theta. That's why sine 2 theta is 2 sine theta cosine theta. That's why. There, I proved it again. So you have to force yourself to remember that we proved most of the things on that top part of the green sheet for sure, except for the law, cosines, law, sines. We haven't gotten there yet, but those look very intriguing. You guys with me? So while I say have the green sheet next to you while you do the homework, that is not to mean don't worry about memorizing it. Have it there to help you start to memorize things, right? Try to get to a point where you don't have to look at it, or try not to look at it for a couple problems and then look at it, just get it in your head. Come up with a way to memorize everything above that black line on the green sheet. You must, right? And I'm about to say something that people take wrong. That's enticing. But what I'm going to say is you need that for calculus. And then some people are like, I'm not going to take calculus. Well, you need that for my damn course. So there you go. But this is pre-calculus. So a lot of what we do is to get you ready for calculus. And the more at your fingertips those things are, the easier calculus will be. You can build on that. You have a firm foundation to build on. One of the suckiest things for me if I teach calculus is to have a bunch of students that don't know any trig stuff. And that happens sometimes. Either it's their fault or they had a bad teacher that didn't force it in their brains. That's the worst thing for teachers and students. Trust me. Okay. All right. Is that all right? So that addresses one question somebody had. That's how 2 sine t cosine t became sine 2t. Okay. So for example, let's see. I'm going to clear all this away. We've done this stuff before anyway, so I'm going to clear that away. Let's see. I wanted to look at, let's see what we got here. Here's tangent 2 theta is 2 tangent over 1 minus tangent squared. So let me write that down. tangent to theta is 2 tangent theta over 1 minus, what, I forgot it already. Can somebody help me out? God, Jeff, I can't even look back at the old 1 minus tangent squared theta, is that what it is? I think so. Man, all right, it's this weird night. You guys are very quiet, and only Jason has got his video on. All right. Now that you know this, what is cotangent of 2 theta? Anybody know? Let me see if you can be careful about this.
Is it just the inverse?
And you mean reciprocal, right? Yes. So the mistake people make is they just put cotangent here. That's not quite right. It's the reciprocal of what tangent is. That's what cotangent always is. By definition, it's the reciprocal of tangent. Now, could I maybe work with this and get cotangent to show up in it? Of course. Do I need to? Probably not. Oh, so now look at this bad boy. So now this has got 2 cotangent 2x. So what's 2 cotangent of 2x? Well, it's like that 2 would come up, right? And I just have to put an x in place of my theta. So pretty cool with what's happening. Do you see how I did that? I want cotangent of a double angle. I got tangent of a double angle, which means I have cotangent of a double angle. Then I know how, then I look to see how can I rewrite this. I didn't do this problem before class started. So when I first looked at it, I didn't immediately know what to do. I just kind of picked this side because it looked like I had the most to do. And another thing to notice is this is a double angle and these aren't. So it kind of makes sense to kind of rip this one down into a single X so that they all have the same angle. That's the only way I can show the two sides are equal. Does that make sense? So it's just another thing to look for. Now I'm one step away from the answer here. Do you guys see? I don't know. I know there's somebody out there going, see what, Jeff? You've written a lot of shit down. And I don't know what the hell any of it is. So this is nothing you have to memorize. I got it from the sheet. This is the definition of cotangent versus tangent. It's just 1 over tangent. Just flip the tangent. Always, no matter what the hell it is. That's, if you know tangent is something, cotangent is the reciprocal of that. It always is by definition. And then my question is 2 cotangent 2x. Okay, so now I can write twice this would be killing that. And I would put an x in place of theta. And then look, what can I do here? What's 1 over tangent? What's 1 divided by tangent?
Cotangent.
Cotangent. And what's tangent squared divided by tangent?
Tangent.
Tangent. And I'm done because that's this, right? So it's a combination of, in an identity, is there something easily algebraic you can do, like foiling stuff out or combining 2 fractions by finding an LCD? Do it. Or is there an immediate identity you see jumping out at you, like the cotangent 2x we just used, or even the sine 2t if you wanted to start on this side? Those are 2 of the most immediate things you look for. Do I see an identity right now, or do I see algebraic stuff to do? How are we doing out there? You guys have got to work with me here. I don't know. We're going to do a couple more, I think. They don't really give you enough. Well, I think it's the next section where there's some more identity proving, because we get even more identities in the next section. Okay.
How do you do like problem 38?
Yeah, let's look at that. Beautiful. I was going to look at that next. Let me clear all this. See how it says the exponent no higher than 1. That sounds like the reduction formula stuff, right? And just to remind you guys, let me see. Did I put the reduction formulas on here? No, because I'm a dork. But remember, it's just this squared. So let me see. I should have realized that. Why didn't I put them down on here? That's too bad for you, Jeff. I think I didn't put them down here because they're basically these. All right. So for example, cosine squared, if you look at this guy or this guy, well, let's look at this guy here. Cosine, sorry, I'm gonna write this down. Oh, somebody's chatting at me. Oh, I'm sorry. Oh, understood, understood. Yeah, you don't have to share your screen. It's fine if weird things are happening. All right, let me write this down up here. So the half angle formula that you have to memorize. Well, I'm sorry, it's not squared. I'm getting ahead of myself. Then if you square both sides and do this at the same time, let me see if you guys are cool with this. Do you see how this has got to be half of this, which is exactly what it is? So what's cosine squared of 5x? If I know that cosine squared of theta is 1 plus cosine of twice theta divided by 2, what's cosine squared of 5x? All right. All right.
Is it 1 plus cosine 5x divided by 2?
No, twice theta. See that?
Be 10x.
So
Oh,
whatever
sorry.
this is, I just double it here because that's what the thing tells me to do, right? I mean, I think these identities are formats to follow. So what this identity says is that cosine squared of some angle is 1 plus cosine of twice that angle divided by 2, whatever that angle is. So what's the angle in this problem? 5x. So it'll be 1 plus cosine of double 5x, all divided by 2. So that's how to use the identities directly. So these problems are using identities directly to simplify expressions. They aren't like proving identities, which is what these are doing. A problem like this gets really disgusting quickly. Can you guys see why? Do I have any formulas for fourth power stuff? No. So what am I going to have to do?
Split it up.
Yeah, so sine squared. Oops. Let me start at this. This is the one you have to have memorized. The half angle formula is plus or minus. 1 minus, because cosine's an asshole. All right, so when it's sine, cosine's like, screw you, I'm going to make that negative. I have no idea. I'm trying to help you. I'm trying to help you figure out how to memorize these things. So then if I square both sides, it gets rid of that stupid plus or minus. That's nice. Let me see. So I get this here, right? And if I do one more thing, just adjust. Let me see if you guys are cooler with this. I don't know if, so if I make this alpha, this will be twice alpha, because what does the rule say? Whatever this is, that's twice that. Isn't that what that says? All right. So what is sine to the fourth 8x? It's sine squared 8x squared. Is everybody cool with that? I don't know how comfortable you are at the moment with power showing up in the middle of things like that. We talked about that before. It's because, for example, if I try to write this as cosine 5x squared, now it looks like the x is squared. So I have to do this, and that's just, we don't want to write that much because we're lazy. Math people are. All right, so let me stop for a minute. The big mistake I see is I'll see somebody say, well, if this is true, then this must be true. And they just put a 4 everywhere they see a 2. No, right? That is not the intent of the form of this. It's the input that's important. Whatever this is, that's twice that. Everything else stays exactly the same. I have no formula for the 4th power. So what would the inside here be? How could I rewrite the inside of this using this? So whatever this is, what goes here, twice that. So how do I rewrite this? Right, 1 minus what?
16x.
16x. Does everybody see that? Whatever that is, if it's sine squared of something, it's 1 minus cosine of twice that something divided by 2. That's just what it is. We've proven that. We proved that before. All over 2, and this is squared. So guess what you got to do? Yeah, buddy. And when you do it, guess what's going to happen? Oh, shit. Now look what I would do. You ready what I would do? I'll show you something kind of neat. Because this looks gross. This looks especially gross because it's a fraction and all that kind of shit. So what am I going to do? I am going to square the 2 and get it out the way immediately. What do I mean? I'm going to do this. Get out of there. I forgot now. What am I going to do? Oh, yeah. I'm going to take a 1/4 out because that's 2 squared is 4. We just get the shit out the way, and then I can focus on squaring that. Now it's much better, and algebraically legal. Right? You're not going to have some knock on the door. All right, we've been watching your activities, and we saw you do something illegal with the algebra. Right? Now, what really sucks about this problem, and you're like, there's more. Can you guys see this in your head to FOIL this out? 1 minus cosine minus cosine minus 2 cosine 16x. But then what am I going to get here at the end? Plus freaking cosine squared. Shit. So I'm going to have to use the cosine formula to break that one down. And then I'll be done. Thank God. So the higher the power gets on the thing, the more little steps I'm going to have to take to reduce the power. So my first step went from a 4th power to a 2nd power. And then my next step is going to take that 2nd power piece and make it a 1st power. Then everything's to the 1st power, right? Okay, maybe I have no way of gauging from little boxes with your names in it how that's going over, but nobody's saying anything. Okay, there you go. Thanks, Doug. I got a little thumbs up in a box now. Step 1, get a box. Okay, let me see. Let me clear all this. Is that all right? I'm going to clear it away. Bye-bye stuff. Bye. Okay. Let's see what else we got going on down here. Yeah, this is the same thing. To check it graphically, you just graph what they give you, and they graph your resultant answer, and there should overlap. They should line up on each other. They should draw themselves over each other. Does that make sense? So it's exactly like these problems. Just they have the extra step of put it in the calculator and check it. So you can always do that, to be honest. All right, and then we're basically done. Okay. All right, so if you haven't, I have a feeling that most of you guys are finishing up 8 right now because nobody yelled at me for not having anywhere to turn 9 stuff in. So you got to get into that 9-1 to try out those identity stuff. Okay. So here's something. Here's some of the craziest shit. All right. So let me show you this. If I took, well, screw it. I'm just gonna, here we go. Notice what they do. So this first equation, that's just the difference of angles formula for cosine. Oh my gosh, how do I make you go away? Just stop. This is kind of neat. This is a little bit neat. The application of this is neater in other areas. But what they do is they add the formula for cosine alpha minus beta to the formula for cosine alpha plus beta, and they notice that these cancel. So what that ends up with, if I divide by 2, I will get what they call a product to sums. So it's the product of 2 cosines, and they write it as a sum of 2 cosines. That is not remarkably, how do I say this correctly? That is important, but it is nowhere near as important as the other ones. That's why I did not make it one that you had to memorize. Will you have to use it in this homework? Hell yeah. Can you go look at it? Hell yeah. If I ask you a question about it on the test, will I give you the formula? Hell yes, because you don't have to memorize it. But you have to be able to use it. That's all. Can you just use it? So let me just jump ahead a little bit. They do that with sine and all that kind of stuff also, and they end up, come on, where are you at? Where's my little, there we go. That's on the green sheet underneath the dark black line because you don't have to memorize it, but you can see why they call it product to sum. You can see that. Now, and I'm really sorry. Normally, I'm very excited about what we're doing. These are a little bit, all right. So take that as you will. And then this one is kind of, I'm not even sure how to convey this to you. This is awesome shit. This is actually kind of cool shit right here, buried inside of not very useful shit. Can you go back and explain it? Oh, I'm sorry. So again, all right, let me go back. All right. So if let me see. If I add these together, and this is not the history of every trig identity, but this is the history of some of them. We just played around with shit. We just played around with stuff. So notice that so here's the formula for cosine of alpha minus beta. There it is, right? Cosine's an asshole, so it makes that becomes plus. And so here that becomes minus. And you'll notice if I just add those together, don't these parts cancel? And that plus itself is 2 of these. If I divide both sides by 2, I end up with the product of 2 cosines equaling an expression involving the sum of 2 cosines. So, for example, let me see, what would be an interesting example? Yeah, let's do, well, I mean, watch this. This is kind of silly. Cosine of 15 degrees times cosine of 15 degrees, right? That would equal 1/2, using the formula, 1/2 of cosine of 15 minus 15, so 0, plus cosine of 15 plus 15, 30. You guys with me? Is my Wi-Fi doing okay? All right, I'm looking a little laggy. And then we can do that, right? Do you see that? There's a concrete example. There's not a lot of concrete examples of angles that come out to be ones that we know. So then I'll get 1/2 of 1 plus, right? Because cosine of 0 is 1. Cosine of 30 is rad 3 over 2. And then you can distribute the 1/2 and, okay. You guys semi with me? So there aren't a ton of places where this makes sense to do things with angles that we can do by hand. This is a useful identity with some higher level trig simplification things. This could be a useful identity if you get to calculus and you're doing some calculus and it's easier to do that calculus to this than it is to this. So you'll take this expression and write it like that and then do the calculus to it. How often does it happen? Not very. And that's why, again, that's why this is not one I make you memorize. But it is important that you can tell how we got to that. This isn't very difficult mathematics that's happening here. Okay, maybe. And again, when you get into the history of math, which I wish I would love to take a sabbatical and create a history of math course, but then I'm worried how many people would go take it? I don't know. Because the history of math is very different from the order that we teach math in. We did a lot of high level shit, considered high level now, that we then discovered lower level shit from. And now we teach it that way. I'm basically doing the hierarchy. We teach it in a different order because it makes sense to do it in a certain order when you teach it. But we discovered it very often backwards. And you have no idea what I mean. I'm sorry. But this type of thing has its uses. It totally did. But those uses have kind of run out now for some of the part. Yeah. All right, that's enough of that. Is that all right? Is that a better explanation there? That was one formula. Where it came from was just combining those two things. That's all. That's where it came from. Okay. And again, do you have to memorize this formula? No, you do not. Are you gonna have to use it in the homework? Hell yeah. Why is that not a problem? Because you can just go look at it, right? You could just go look at it. Okay. Blah, 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 blah. And then there's the sine stuff, same idea. Yeah, I agree, Sylvia. So, yeah, I try to throw in some of the history when I can. But I agree with you. Overall, we need to work more of it in our curriculum. Unfortunately, I don't know if you guys have noticed that 176 is chock full of content. Have you guys picked up on that? So can you imagine me trying to throw, like, as a part of the curriculum, historical little pieces? So I'll try to throw it in as like interesting little tidbits when I have something to tell you. But to be honest, I haven't looked at the history of this in a while. I can vaguely remember this being more important before, but that's all I remember. All right, let me see what else is something interesting. So they go through, and there's the culmination. That's on the green sheet. All these are on the green sheet. Blah, 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 blah. And again, so so let's look at this problem here. Cosine 3 theta, cosine 5 theta. You write it up here again. Cosine of 3 theta times cosine of 5 theta. So that's obviously using this guy. So how do I rewrite this? It would be 1/2 of cosine of 3 theta minus 5 theta plus cosine of 3 theta plus 5 theta. And what's cosine of negative 2 theta, for example? What can I do with the negative? It just goes away. Do you guys remember that? Now, the part that really makes me cry is if a student says this would make me really cry. That's sort of like saying square root of 2 plus square root of 7 equals square root of 9 equals 3. Yay, Jeff. No, stop it. Right? You can't add the insides of a function like that. In fact, here's something interesting. Here you go. You ready? Here's something interesting. If I do have a function where f of x plus f of y equals f of x plus y, that is called a linear function because it looks like the f was factored out, like I can do with the linear. So it's called a linear function if it has that property. So square roots definitely don't have that property. Cosine and all the trig functions don't have that property. All right. So let me clear all this. So I'm trying to walk a fine line here. These are important to use. It's important to get used to how to use the form of a formula, right? These specific formulas are not as important as some of the early ones in general, but the idea of how to use a formula is important. And that's why I assign these problems without feeling too bad about it. This one I was about to do, and then I think we'll call it a night. This is really kind of cool. I mean, this really is. And again, if you don't agree with me, that's okay. But this idea, this is a very funky idea. But this exact way of doing things is used quite a bit in some other higher level mathematics. So why are we doing this? Well, we're going to see down here later. But if I define alpha to be u plus v divided by 2 and beta to be u minus v divided by 2, then you can see what alpha plus beta becomes, and you can see what alpha minus beta becomes. Now, is that something you would come up with on your own? Probably not. And in fact, you currently don't even see the importance of that. I don't blame you because I haven't gotten to it yet. Then down here, we know this first thing is true from earlier. This is just a sum to product formula. Then I replace alpha with this and beta with this. And then I can rewrite this. I bring the 2 back over. I multiply both sides by 2. So now I get this equals this, which is all remarkably interesting. I mean, so in the end, let me just show you. So this is a really cool thing, but it's used for such a ho-hum kind of thing here. I end up with these. So this, what did we have earlier? What did we have up here? We had product to sum formulas. What do we have down here? We have sum to product formulas going the other way around. And why did we have to do that nifty little thing? Because I want the insides of these to be written directly in terms of both of these. So if I have sine of an angle plus sine of some other angle, I can rewrite it as a single, what do you call it? A single term, a single, yeah, connected by multiplication. Why can't, do you guys see why, remember this? What's 2 sine theta cosine theta equal to? Somebody remember that from earlier? Sine of, man, you guys are overloaded. I can feel it. You're like, this is the way it is, guys. These are identities. We got to get used to them. This whole section, though, I will agree with you. The formulas are not as integral, but you do have to know how to use them. So remember this from earlier, right? 2 sine theta cosine theta equals sine 2 theta. Why can't I use that on this? What's got to be true about the angles?
They're different.
Yeah, these 2 angles are different. I can't use that. Good, thank you. It's the same thing as what's sine squared theta plus cosine squared theta? What's that?
1.
1. But what's sine squared alpha plus cosine squared beta?
No idea.
No idea. It's just it's that. That's all we know. Okay, thank you. Good. I like it. All right, let me clear these away. So the point of this section of homework is not to memorize these. It's to be able to just use them. So let's look at real quick. I said, so down here you got some product. They even tell you evaluate the product using a sum or difference of 2 functions. So that's product to sum. Then you can go look the appropriate one up. You want the one that's cosine of alpha times cosine of beta. You look that one up, you use it. You put the 45 and the 15 in the correct places. Are you guys with me? And that'll be one you can do because 45 plus 15 is 60 and 45 minus 15 is 30. So you'll end up with something you can do by hand. Then you got these. These will be sum to product formulas. It's crazy. So you find the sine alpha plus sine beta, and you use that formula, and they put the things in the right places. So it's not terribly high level stuff. You just have to be able to use the formulas correctly. And I do want you to get used to how trig functions kind of like interact, even with the stuff that you don't have to memorize. And then you have some identity proofs. These are going to be some of the more interesting ones. But again, so for example, number 33, do you see how there's a product there? And on the other side, there's a difference. Stop it. So I probably could start on this side and look up the sine alpha, cosine beta, and use that identity and just start attacking it. So I want to look for identities I can work with. All right, some of those are going to be fun. All right, I like it. This is a little too far in the future. I think some of you guys are just starting chapter 9, if anything. So these will be in your future. By the time you get to these, you'll have a few identity stuff you've done under your belt. So I'm hoping these won't be as evil, though they are using some more obscure identities. All right. I think that's enough. You guys seem pre-calced out. So I'm not going to try to shove more of that in your brains. And now you're in a perfect place to go do the quiz immediately. No, maybe it's a good thing I gave you till Wednesday morning, so you can kind of decompress tonight if you need to after today's lecture. So let me know if you have if you need to hang out. Otherwise, you are free to go away. Cool. And if you want to start the quiz, go ahead. You can have until Wednesday morning. I think I made it 7 a.m. All right. I'm out of here. Take care, guys.